Hi and welcome again. In this video lecture we are going to talk about the Laplace transform. So far we have been focusing on this line of work. So we start with physical dynamical systems, with some dynamical systems, and using some modeling tools like laws of physics, for example, we are able to derive differential equations or integral differential equations that describe this dynamical system in terms of input and state variables. These equations can be nonlinear, and we know how to linearize them at equilibrium points using Taylor's approximation theorem. So starting from a dynamical system, we extract nonlinear equations, which can then we linearize, and we end up with some linear differential equations. Now the question is, what can we do with these differential equations? How can we solve them? How can we, in other words, simulate the dynamical system? And what properties can we deduce from these differential equations about the trajectories of the system? To put it differently, we have an ordinary differential equation, a linear ordinary differential equation, which we know that it looks like that. And now the question is, given an input signal u, given an input signal u, which is a function of time, it is a function that takes us from the time variable to r. Let's say that we only have one input variable, we don't have vectors here, just single inputs and single state variables. So given such an input, how can we determine a trajectory of the system, a function x of t, a function x so that this function x together with this function u satisfies the differential equation of the system? In other words, how can we go from a linear differential equation to determining a solution? It turns out that this is generally very difficult to do, especially even for linear differential equations, especially given the fact that we have an arbitrary input. We want to be able to simulate the system, to tell what the system behavior will be for any such input signal u. This turns out to be a very difficult task. The Laplace transform will allow us to do the following: to take such linear differential equations. And let me say at this point that what makes these equations difficult is the fact that they are differential equations. But differential equations can be difficult. Algebraic equations are a lot easier. So the Laplace transform is a new concept that will allow us to map linear differential equations to algebraic equations. These now are much easier to work with, and they allow us to determine solutions by taking the inverse Laplace transform, by undoing the Laplace transform, which is also possible. So in this lecture we are going to define the Laplace transform and study a few of its properties. So first things first, a function f from the non-negative real numbers to the real numbers is called a time domain function. For example, this function is a time domain function, is a t domain function. It is defined only for non-negative times. It is not defined here. Okay, such functions are called time domain functions. And some of these functions have a Laplace transform. So let f be a real valued time domain function. By the way, we can rewrite the same definition for functions which are complex valued. We can extend this definition, if we like, to functions f that take a time parameter t, which is non-negative, and map to the complex field of numbers. So this is a time domain function. The function L calligraphic of f, a new function that maps the complex numbers onto the complex numbers, defined by this integral from 0 to infinity exponential of minus s tau f of tau d tau, where tau is the integration variable and s is the argument of this new function. So s is a complex number defined by this integral. Of course, defined for, perhaps not for all complex numbers. Often it is not defined. Usually it's not defined for all complex numbers. It is defined over a set A, which is a subset of the set of all complex numbers. So for all complex numbers S, so long as this integral is well defined and converges, I will explain in a second what converges means, then this new function is called the Laplace transform of f. So what we are defining here is the following thing. You have the set of all possible time domain functions. Here is where time domain functions live. Some of these functions, not all of them, some of these functions have a Laplace transform. Let's call these functions Laplaceable functions. And of course, these are time domain functions. Now the Laplace transform takes such a function f and returns a function LF, L calligraphic of f, which has a domain A. A is a set of some complex numbers and returns a complex number. So given a function, the Laplace transform provides another function. The first question, which we'll not address in this lecture, is what is this set here? Which functions have a Laplace transform? Are there any functions at all which have a Laplace transform, or is this never well defined? It turns out that a very large class of functions have a Laplace transform, and we will give several examples today of functions that do have a Laplace transform. The good news is that most functions that we will need to work with do have a Laplace transform. So let's give an example, example number 1. So example number 1 goes like that. So recall that the Laplace transform of a time domain signal f, of a time domain function f, is given by this equation over here, the integral from 0 to infinity exponential e to minus s tau f tau d tau, what is the Laplace transform of this very, very simple function, of this function over here. The constant function, all right? This is constant and it is equal to 1. So let's take the definition. Laplace of 1 is a function of the complex variable s. S is a complex number, and according to the definition, exponential of minus s tau times 1 times d tau with respect to tau. When we say the integral from 0 to infinity, what we actually mean by infinity here, let me explain what this infinity means. It means that we have to take the limit of a variable t uppercase, which goes to infinity, and then have the integral from 0 to that variable t e to the minus s tau d tau. So this is what infinity here stands for. This is the definition. And so long as this limit converges, this is what we meant before by saying that the integral converges. So long as this limit converges to a finite value, we say that this integral converges, or it exists. Okay, so this is the limit. Now what about this integral over here? This is equal to 1 over minus s, which is the coefficient of the integration variable, so minus 1 over s, times the function itself. Let me explain this very quickly. This is because of the following property. So an antiderivative of e to the a tau d tau is 1 over a times this function plus the integration constant. Here we have a definite integral from 0 to t, so it is e to the minus s tau from 0 to t uppercase. When we say from 0 to t uppercase, so when we say from, let's say, from x to y, a function f tau d tau, we defined the other day that from the fundamental theorem of calculus, if function f lowercase has an antiderivative f uppercase, then we can do f y minus f x. F evaluated at the upper limit minus f uppercase evaluated at the lower limit. Or we can write this, it's often convenient to write that this is f and then a line here from x to y. And this is what we have here. So this is the value of this function evaluated at tau equals t uppercase minus the value of this function evaluated at tau equals 0, from 0 to t uppercase. So this is now equal to the limit. T goes to infinity again, and we can take this outside, minus s t uppercase. And look here, e to the minus s times 0 is e to the 0 power, which is equal to 1. So now what is the limit? The question is, what is the limit as t goes to infinity? And let's suppose just for a second that s is a real variable. It's a real valued variable. It's not, by the way, it is a complex variable. But let's say it's real. Then what happens? Then the exponential function e to the minus s t uppercase can be either like that, goes to infinity, or it can be like that, goes to 0. So this is e to the minus s times t uppercase when minus s is positive. So this is when s is negative, it goes to infinity. And this is the function e to the minus s times t when this minus s is negative. So this is when s is positive. So in one case, this function converges as t goes to infinity, converges to 0. Let me write it down. If s is positive, then this whole limit, the limit t uppercase goes to infinity, minus 1 over s e to the minus st uppercase is equal to 0. But if s is negative, then this limit diverges to infinity. So it is not desirable to have things like that. Otherwise, this will be equal to infinity and this doesn't make sense. Instead, we can say here that if s is a real number and s is positive, then this is equal to, this goes to 0, so it will be minus 1 over s, 0 minus 1, and the answer is minus times minus plus 1 over s. So we can say, we can pretend that we solved the exercise, and we can say that the Laplace transform of the constant function 1 is a function of s, which is 1 over s. But we haven't provided a complete answer, because we said, we assumed here that s is a real number. It is a complex number. So how do we treat now complex numbers? Say that s is a complex number, so s must be equal to some a plus the imaginary unit, we'll denote it here by j, times b. And the limit will be minus 1 over s here, so this first part. So instead of s, we have written a plus jb. And we can break it down now. And the limit is written like that, this part times this part. It is not still obvious what to do with this limit, but it becomes really very easy to deal with if we take here the modulus of this complex number. The modulus is like the absolute value of a number. And here we have the modulus, which can be written as the modulus of the first times the modulus of the second times the modulus of the third. This is the property modulus of a product is the product of the moduli. So now this becomes, I will take the modulus of 1 over s outside, and I will have the limit, t goes to infinity, the modulus of e to the minus a t times, and the modulus of j times something. This is another very useful property of complex numbers that we will be using all the time in this course, is that the modulus of e to the j z, let's not call it z, jb, let's say, where b is a real number. So the modulus of e to the power of an imaginary number is always equal to 1. So this is equal to 1. So this is the limit of this term over here. And as we discussed previously, if a, now a is a real number, okay? So this is either equal to infinity if a is negative, or to 0, this is 0, if and only if a is positive. So before we proved that when we restrict our analysis to real numbers, we proved that the Laplace transform of 1 is 1 over s for all those real numbers which are positive. And now we showed that this is true again. This is 1 over s, because this is 0, and this is minus 1, 1 over s again. For s which are complex numbers, for all a which are positive. But what is a? A is the real part of s. So we can write for all complex numbers s whose real part is positive. So once again, the Laplace transform of the constant function 1 is a function of s, which is 1 over s for all complex numbers with positive real part. Okay, let us have a look at another example. The more examples we do and the more exercises we solve, the more confident we will become about using the Laplace transform, and we will learn its definition naturally. So example number 2 is what is the Laplace transform of the Heaviside function. The Heaviside function is the following function. It is a time domain function. Before some time, let's call it a switch is off, and at time a, the switch turns on, and we can write it mathematically as follows. It is denoted by h, as in Heaviside, with parameter a, with subscript a. And in some cases you might see that this is defined by t smaller than or equal, or like that. This doesn't matter, because the Laplace transform of the function with less than is exactly the same as the Laplace transform of the function with less than or equals. So now the question is, what is the Laplace transform of this function? This is a very popular function in control theory and in systems and signals theory in general. So let's solve it. The Laplace transform of the Heaviside function is a function of the complex variable s. S is a complex variable. And now we have the integration variable tau. Tau goes from 0 to infinity, and this Heaviside function is equal to 0 for tau between 0 and a. So if I plug here, let's write it down like that. I can split the integral from 0 to infinity, from 0 to a, plus from a up to infinity. But this function here from 0 to a is equal to 0. So the first integral is 0. And the second function from a to infinity, from a above, so let's write here that this is equal to 1 if t is above a. So from a up to infinity is equal to 1. Therefore the integral now becomes equal to the integral from a to infinity of this function. And we can write again so it is from tau equals a up to tau equals t, and we take the limit as t goes to infinity, minus 1 over s. This term I can take it outside, and then I have e to the minus s t uppercase minus e to the minus s a. And this is now equal to, now this goes to 0, but it only goes to 0 if s is positive when we're talking about real numbers. Otherwise we must say that the real part of s is positive. So this only goes to 0 if the real part of the complex number s is positive. This is exactly identical to what we discussed in the previous example. And we have that this is equal to e to the minus sa divided by s. Let me write in red color for all those complex numbers s with a real part which is positive. Now, in summary, so far we have proven that So far we have proven that if function f of t is equal to 1, then the Laplace transform of this function is 1 over s, defined for all complex numbers with a positive real part. And similarly, the Heaviside function h with parameter a has a Laplace transform e to the minus as divided by s. And again, this is defined for all complex numbers with positive real part. Now, let us do one more example. What about e to the at? What is the Laplace transform of the exponential, and for what complex numbers is this defined? So example number 3, what is the Laplace transform of the exponential function? Of course, when we say the exponential function, we mean this function, f of t, defined for non-negative times t, and we can plug this function in the definition, and pretty much business as usual, we'll solve this exercise as well. Absolutely nothing new, this is just to practice now. So the Laplace transform of this function is a function of the complex variable s, which is the integral from 0 to infinity I combine the two terms over here. Now this is, we know how to evaluate this definite integral from 0 to t is the integral of an exponential function, and this is equal to itself divided by the coefficient here. And this is a definite integral, so we will go from tau equals 0 to tau equals t uppercase. And now, pretty much as we did before, this integral, especially as t goes to infinity, let me write it down more explicitly. So this is e to the a minus s times 0, so e to the 0 power. So just let's write here 1. And this term either goes, the numerator either goes to infinity if a minus s is positive, or rather, if the real part of a minus s is positive, then this diverges to infinity, then this limit is equal to infinity, or if this is negative, then this converges to 0. This converges to 0. So if we assume that the real part of a minus s is negative, this is 0 and then minus. So in other words, 1 over s minus a for the real part of a minus s being negative, but this a is a real number. A here, we took it to be a real number. So equivalently, we can write a minus real part of s is negative, equivalently. And it's not over yet, but let's write the result here. So exponential to the power at is 1 over s minus a, and this is defined for all those s which are complex numbers with a real part above a. And you can see here that we are compiling a table where we have a column being signals in the time domain, then the Laplace transforms of these signals, and the domain of the Laplace transforms. And we can keep doing that until we have compiled a table of the Laplace transforms of the most useful functions that we will be dealing with. So we can do, for example, function t, we can do t squared, and we can of course do functions like sine and cosine. And this should be enough for today actually. So let's start with function t. The black one is out of ink, so I will continue with the blue one for today. Okay, so next problem is the following. Function f of t is equal to t for all non-negative times t. Find the Laplace transform, which is a function of the complex variable s. And of course, we need to find both the Laplace transform and the domain of the Laplace transform. So business as usual again. We will use the definition of the Laplace transform. We're doing this to exercise mainly. So it is the integral from 0 to infinity. So our function tau and we have tau times an exponential function, and we know from calculus that to solve that integral, to find the value of that integral from 0 to infinity, we need to use one possible solution is to use integration by parts. So integration by parts, recall, that is the following formula. When we have an integral, a definite integral from a limit a to a limit b of the derivative of a function times another function, it's not clear yet what is that derivative and what is function f and what is function g, but we'll discuss about that in a moment. So the result is, and this notation here, fg from a to b, means f times g evaluated at b minus f times g evaluated at a. And we have taken the derivative from one function, and we have on the right hand side of the equation, we have moved it to the other function. So let's think for a moment. If this function, e to the minus s tau, is the derivative of another function, if I can write this as a derivative, then if I apply this formula, it will be the other function, namely tau, on which I will move the derivative. And if I do so, the derivative of tau is equal to 1. So I will hopefully have simplified the result. So this function, e to the minus st, can be written as follows. It can be written like that as the derivative of another function. And now I can define this to be my function f and this to be my function g. And I can apply integration by parts. I hope you have written it down on your notebook so I can erase it. However, just one little detail here, integration by parts applies to integrals which are definite integrals from a finite limit to another finite limit. It doesn't exactly apply, at least as we wrote it down previously, to limits that are equal to infinity. But we can simply do the following. Write the limit outside, just to be very correct here. That is from 0 to t uppercase, where t goes to infinity. But inside the limit now we have a definite integral from 0 to t uppercase. And there is no tau here because we have taken the derivative. Let's write it down. We have taken tau derivative. But this is equal to 1. Very good. Let's write this out. So we have minus, another minus, so it is 0 times that, so this is 0 over s, so this whole thing is 0. Of course, s is not allowed to be equal to 0 here. It makes perfect sense to assume that. And now we have this integral where we have minus and another minus. We can simply write plus over here to simplify things. 1 over s is not a function of tau, so we can take this out. Here we have the integral from 0 to t uppercase. And we have this integral, but we know that this is equal to the following. Let's take things step by step over here. Let's write it again. So this is equal to what, this first part? T goes to infinity, and this goes either to infinity if s is negative, or if the real part of s is negative, or goes to 0 if the real part of s is positive. This is something we discussed in the previous examples. And now we have assume here, assume that the real part of s is positive. Then what happens? Then this goes to 0. And then we have t times an exponential. And we know that when the exponential goes to 0, then t times the exponential also goes to 0, because the exponential goes to 0 much faster than t goes to infinity. But you can prove that as an exercise. Let's write it here, exercise. Prove that the limit of t uppercase times exponential minus t, as t goes to infinity, this goes to 0. This is the property we're applying here. Okay, so this goes to 0. This is equal to 0, so 0 plus 0 is 0, and then minus 1 over s. What is this integral? It is minus 1 over s e to the minus s tau, from tau equals 0 to tau equals t uppercase. And I will skip a few steps here. This is also an exercise for you. It's an exercise because you will be applying exactly the same procedure as we did in this example as well as in previous examples. And you will find that you have 1 over s here, and this will be again equal to 1 over s under the assumption that the real part of s is positive. So this is 1 over s squared for all those complex numbers s with a positive real part. And I can write it here now. And we're filling in the table of Laplace transforms. For t squared, the answer is 2 divided by s to the third power with this domain. Now we will do sine and cosine. This will be the last example for today. This will be slightly different. We have that f of t is equal to sine omega t. So we want the Laplace transform of this function. What is the Laplace transform of this function f? And we also have g of t. What is the Laplace transform of cosine of omega times t? One possible way, of course, to go about it is to take the Laplace transform, start with the first one, take the sine. What is that? This is the integral from 0 to infinity. And you can actually solve that by applying the integration by parts procedure on this integral. It is an exponential times sine. And once you finish with that, you can do the same for cosine of omega t. But this is a little tedious and most importantly it's boring because we will be doing exactly the same thing. So let's think a little differently this time about this particular example, and this is a very elegant way of solving this exercise, but also it provides some very useful insights and a little trick that we can reuse, and we will be using a lot in this course. It is all a result of the following very useful identity, an identity related to complex numbers. So when you have e to the j z, then this is equal to cosine of z plus j sine of z. What about it? How is that useful here? The thing with this equation is that it provides a link between sines and cosines and the exponential function. And here we have already derived the Laplace transform of exponential functions. So the question is, can we use this formula to derive the Laplace transforms of sine and cosine directly from this result? That would be great actually, because we won't have to solve any integrals at all. And when it comes to solving any problem involving sines and cosines, do recall that there is this formula that links sines and cosines with exponentials. Often it is more convenient to work with exponentials rather than trigonometric functions. And in other cases, fewer, I think, it is more convenient to work with trigonometric functions. But let's see how this plays out here. What if we apply the Laplace transform on both sides of this equation? And we're mainly interested here in z equals what? Omega times t. Let me write it down again. So there it goes. We have cosine of omega t and sine of omega t, which are these two functions, in one very neat and simple equation. Let's apply the Laplace transform on both sides. And we have here the Laplace transform of the sum of two functions. We can show, actually you can do that very, very easily, that if function f and function g have a Laplace transform, then we can do the following. This is an exercise. If both f and g have a Laplace transform, so if LF and LG are well defined, then we can do that. We can apply the Laplace transform, or the Laplace transform of the sum is the sum of the Laplace transforms. So equivalently, and look here, we have this j. This j is a constant, it's not a function of t. Therefore, we can take this outside. Why? And here comes another property, a very interesting property of the Laplace transform. So exercise. If function f has a Laplace transform and a is a constant, then I can take this constant outside. So let me write it again. If the Laplace transform of a times f is a, times the Laplace transform of f. This is very easy to show. Just write down the definition and you'll be able to see why. So I can take j outside. Let me, in fact, move it outside right away. And now, what is the Laplace transform of the exponential function? It is, first of all, what is the coefficient here? It is j omega. J omega. So it is 1 over s minus j omega. And this is equal to, it is the Laplace of the cosine plus j, the Laplace of sine. On the right hand side we have a complex number, something plus j times something else. And this is the real part of the complex of this complex number. And this is the imaginary part. When you have a complex number z, z is a complex number, you can write it like that. Z equals a plus j times b. A is called the real part and it's denoted like that. The real part of z, Re of z, and b is the imaginary part, Im of z. What is now the real and the imaginary part of the number on the left hand side? Let us multiply by s plus j omega the denominator and the numerator. Of course, this implies that s is not equal to j omega. And of course, it implies that s is not equal to minus j omega. And this is equal to the right hand side. And there is not enough space, so I will erase this part up here. So this is, if you do the math here, it is s squared plus omega squared. And this is equal to, and I will write it once again just to see it very, very clearly. I will write this number in this form, a plus jb. So I will separate the real and imaginary part. Here's the answer. Can you see it? It is here we have the answer for both the sine and the cosine of omega t. Let's write it like that. What about now? Now it should be clear that this is equal to that. And the red parts are equal to one another. So let's write it down. So the Laplace of sine of omega t is omega over s squared plus omega squared. And then the Laplace of cosine is s divided by the same denominator, s squared plus omega squared. Let me write it here in the table. And this completes the table of Laplace transforms that we need to know. Now, what is the domain of each of these Laplace transforms? I will leave this to you as an exercise. We gave a hint over here that s is neither j omega. It is not allowed to be j omega and minus j omega. We did sort of a logical leap here in solving this exercise because we used the Laplace transform of e to the at and we did Laplace transform, we applied it to the Laplace of this function. This is a function f. Which function f? It is function f equals j omega t, which is a function. It is a time domain function but it is complex valued. But here we did the proof for a real valued function. So to be perfectly correct, we should have performed this proof for complex valued functions where a is allowed to be a complex number. All right, but you can actually do the proof for complex numbers. Nothing changes much, only the domain. And then we would be able to write down, we would be able to derive the domain for sine and cosine. Let me say it once again. We started the proof for showing that the sine and cosine have these Laplace transforms by using we did the proof for the sine and cosine, for the Laplace transforms of sine and cosine using this formula over here. And then we took the Laplace transform on both sides. We said the Laplace transform of this is the Laplace transform of the right-hand side. Therefore, we applied the Laplace on the following exponential function. On this function. This is a function f of parameter t, which is t's time, so t is non-negative, but this function is complex valued, it's not real valued. Therefore, we correctly said that the Laplace transform of that is 1 divided by s minus j omega. This is correct, but we didn't prove it. So what you can do to find the domains of sine and cosine, of the Laplace transforms of sine and cosine, you need to do the following as an exercise. To answer this question, what is the Laplace transform of the exponential function e to the at? Didn't we do that here? We did, but this time in this exercise, solve it with a being a complex number. This will be the same result. This will be slightly different. The domain will be written in a slightly different way. And then you will be able to answer, to fill in these boxes. What is the domain of the Laplace of sine and what is the domain of the Laplace transform of cosine? So in today's lecture, we filled in this table of fundamental and essential Laplace transforms of these function. This is essentially all that we will need in this course. So it is 1, 2, 3, 4, 5, 6, 7. You need to remember these 7 Laplace transforms, and these will be very, very useful in solving problems, not only in this course, but also practical problems in control engineering practice. So this is it. This is everything for today. Thank you very much for watching, and until next time, goodbye.